AQA, A-level physics, the engineering option. Video number 3 is on rotational motion. So this is the bit of the specification that we're going to be looking at in this video. Now look at this. This isn't rotational, this is linear. Hopefully all of this is familiar. If you've got an object of mass m, there's a resultant force F being applied to it. It's got initial velocity u, final velocity v, its acceleration is a, its linear displacement is s. All of this should be very, very familiar. You've learnt your Suvat equations, haven't you? Now, if all of that's in your head, look at this. This is an object. And it has a moment of inertia, I, and we are applying a resultant torque, a resultant moment to it. And because of this, there's going to be an angular displacement, theta. There will be an angular velocity, which is delta theta over delta t. Initial angular velocity, W1, final angular velocity W2, angular acceleration delta omega over delta t. So look, it's the same, it's just different symbols, and one of them's linear, the other one is rotational. I will mention one thing at this point. This omega is delta theta over delta t. That would tell you the average angular velocity over a period of time. If you wanted to know the angular velocity at an instant, then that would be omega is d theta dt, okay, which is the gradient of the graph, d theta dt. That's at an instant. Delta theta over delta t is over a period of time. The same thing down here. The angular acceleration at an instant in time would be d omega dt, which is the gradient of the graph, the rate of change of omega at an instant, but over a period of time. And we're actually going to use this in a question later on in the video. Over a period of time, it's just the change in omega over the time. At an instant, it's d omega dt. Hopefully you do A-level maths, you understand the difference between them. Important point on this slide is that everything's analogous. Look, they're so similar, these two. And you've learnt these, haven't you? You must learn your Suvat equations. I'm not going to talk through them. They should be very, very familiar. Well, how about these? And again, instead of v is u plus at, it's omega 2 is omega 1 plus alpha t, etc. So, look, wow, this is so similar. And this is one of the reasons I think this particular option is the easiest. Once you get that in your head, everything else just falls into place. I mean, we've already done kinetic energy, half mv squared, a half I omega squared. Later on, we'll do momentum as well. That's very, very similar. If you get to do some experiments in class, or at least stuff demonstrated to you, you'll probably use a pulley or a flywheel rather, that looks something like this. This is kind of science equipment, physics science equipment flywheel. And it has a mass of about just over a kilogram. Its radius is about 60 millimeters. It's usually screwed to the wall, and it has a pulley on it so that you can put a bit of string around the pulley and apply a torque, and then you can make lots of measurements. Don't worry about these numbers now, maybe later. Here's a question I'd like you to have a go at. Pause the video, pen, paper, calculator. I'll show you the answer in 3, 2, 1, and there you go. So for the angular acceleration, just delta omega, change in omega over time. In this case, it will be uniform. And then for the angular displacement, you'll see I've used one of the angular equations of motion, and I get 60 radians. Okay, this is very similar to an exam question from not so long ago. A graph of omega against time. The graph represents the rotational motion of a flywheel. Calculate the angular displacement and the angular acceleration during each of the 3 stages. So from 0 to 10, from 10 to 20, from 20 to 40, work out those 2 things, pause the video, pen, paper, calculator, and the answers are 3, 2, 1. There we go. So pretty straightforward. I think there's one tricky little thing, which is the angular acceleration on the 3rd part of the graph, delta omega over delta t. Now omega here is 4. Yeah, it's plus 4. Omega here is minus 2. So delta omega is going to be minus 2 minus 4, which will be minus 6 over a period of time of 20 seconds. So minus 6 over 20, which is how we get minus 0.3 radians per second squared. Just to briefly talk about what is this flywheel actually doing. Well, it's at rest to begin with, and then it speeds up, and then it's spinning around quite fast, and it stays at that rotational speed for a while, and then it slows down, and then it stops, and then it starts spinning the other way. Okay. Right, here's another question. Difference with this one is that the angular acceleration isn't constant. So the graph shows how the rotational speed in RPM, revs per minute, of a wind turbine varies over a 20-minute period. Have a go at the questions yourself. I'll show you the answer in 3, 2, 1. Okay, so from RPM to radians per second, a rev is 2 pi divided by 60. So pi radians per second, then 3 pi radians per second. The angular acceleration, average angular acceleration, is the difference in omega divided by the time. 5.24 times 10 to the minus 3 radians per second squared. The area is the angular displacement, and to get the angular acceleration at point x at that point in time, you would get the gradient of a tangent at that point.